Okay, good morning. This is Haeun Chung. I'm an assistant research professor at Stewart, and this is, I think, my fourth attendance to this symposium, maybe our third talk, so I'm always pleasant to be here. And today I'm going to talk about mission concept, so I'm going to pretend that I didn't read any news article this morning, so wish me luck. So today, obviously, the talk I'm going to give is about mission concept called GlowSat. It's a 6U CubeSat mission concept for far UV airborne line detection. And trust me, I asked AI to make that cell-like shape as 6U like 5 times, but it didn't work. That's why it has CubeSat shape. Anyway, I'm an astronomer, very greedy astronomer who always seek for like challenges and want to detect something faint and stuff. And one of my interests is the detection of the CGM and IGM, which stands for circumgalactic medium and the intergalactic medium, which are actually one of the major mass budget components for the galaxies located around and between the galaxies, the building blocks of the galaxy evolution and the stars. So we would like to know the more details and characteristics of the CGM, IGM, so that we can better understand their inflows and their interaction with the star formation and the galaxy evolution. And the challenge is that these CGM and IGM emissions are very faint. I put that here, the 10 to the minus 20 numbers there, which is like 1,000 times fainter than what you have observed or were able to observe in the previous or existing missions. So observing these emission gas components are really challenging. So I'm keep thinking that what are the missing piece or the technology or the information that will enable us to detect those faint CGM emissions in the future missions. And this is one of the missing component, which is the impact of grading scatter by the airborne lines. So here you see the grading elements, which is the light dispersive elements making like rainbows. Reflecting light at particular angle depending on the wavelength. So in either word, when one wavelength comes in, then it should be reflected to a particular direction. But in the real world, there are like some other lights going to different direction, the scatter light. And the challenge is that in UV, in like low Earth orbit, we have what we call aurora lines or the aurora lines, which are the sky background. So using the spectroscopy, you can separate those aurora lines from your science emission, as you can see on this figure on the different part of the detector. However, with the scattered light, they can pretend to be the CGM emission and can overlap and swamp your precious science signal if the scattering amount is quite significant. So of course, there's ongoing effort to make, let's say, better grading, so that which has better scattering performance, so that that wing component could be smaller than what we want. But another component for the total amount of scattered light is, of course, the intensity of the airborne lines itself. So for the planning for the future mission, we need to know about this airborne line intensity as well. Otherwise, the planning for the detection of this faint emission is not trivial. And this is another figure that I put into my proposal, showing what could be the impact of these airborne line scatters with some simulations. So basically, the bottom two figure shows that in case this airborne line strength is high, then your science emission line could be just swamped into the noise from the scatter light, which is the left bottom left figure shows. But if they are low, then you can detect. So knowing the intensity of the airborne lines is critical for this detection. And then you may wonder that, okay, where I said this is like sky background, the sky emission line emitted by the atoms in the upper Earth atmosphere. So why shouldn't we already know about them very well? Which is not the case. That's why this concept has came. So if we like search for the strength of these algorithm lines in the web or the literature, then what we will see is something like this from the Hubble Space Telescope information. The strength of these algorithm lines are well, only qualitative. You can see the strength is mentioned as SVW strength, strong, very weak, etc. So it's really difficult to like quantitatively estimate the impact of these algorithm lines using the available information. And there is more complication because these algorithm strength is varying in orbit depending on, let's say, the geometry between the sun, Earth, and your spacecraft. And the complete survey or the better understanding of this behavior has not been done. So basically, these intensity distributions of the UV algorithm lines are critically underexplored. So we need to know about this better so that we can plan for the really challenging faint CGM emission detection. So here comes the GlowSat. For the purpose, I come up with this mission concept so that we can we can map the distribution of these algorithm lines. Here is the spacecraft CAT model, and the mission concept is where it turns out that we can do this with only 6U CubeSat form factor. So the concept is doing a spectroscopic mission to map far UV algorithm lines in various spacecraft Earth Sun geometry so that we can construct a foundational baseline for the future UV missions. And along with, of course, with the small CubeSat, we can also advance the technology for the far UV astronomy, the coding, grading, and the detectors as well. So we have a small team so far. Again, this is only concept. Here at GlowBay, myself, Carlos, and Erica, and we have collaborators at outside, Caltech and Goddard for the grading and the coding technologies. And we did propose this mission to the most recent NASA APRA AO back in February this year. And here is where my last slide showing the core of our instrument, the CubeSat. So we have, I have put like this optics into a 2U volume, the payload volume in the 6U CubeSat, and enabling the far UV spectroscopic observation within a bunch of mirrors and gratings. And this is the combination of UV telescope along with the long slit UV spectrograph with a quite large field of view so that we can survey the large area at the same time with distance sensitivity to detect the algorithm lines. And we want to do this on a little bit of unconventional orbit, which is high inclination non-sun-sync orbit. And this is to allow the orbit to precess so that we can cover the larger Sun-Earth spacecraft geometry over short mission period. And this is my favorite part. So these are the like simulated image of the algorithm lines on the detector plane. And where we designed this mission with mind that it's going to be the students, it's going to be enabled by the students. And the optical design has made to be really tolerant to the like misalignment. So here the left image is the spectrum image with nominal optical design, and the right side is with worst case Monte Carlo simulation with like half millimeter decenter or the half degree tip tilt, which is huge. But even in the worst case, you cannot distinguish between those two. So this is to like make this mission happen with the student workforce as well. And if selected, then we would like to, of course, do this with the folks around in Arizona, Tucson, and the UA, and work with UASI to enable this mission in the real world once we are selected. And thank you for your attention. I will take questions.
Hi, yeah, I'm curious if you had any thoughts on your observing plan. Are you planning to do a survey of different pointings through the atmosphere? What are you thinking?
Yeah, so that's a great question. So we don't have like detailed observation plan yet, but our goal is survey the geometry space between a whole geometry space between Sun, Earth, and the spacecraft. And these ergol lines is also depending on like at particular orbit location where you're seeing. So another angular space to survey is where the pointing of the spacecraft with respect to the Earth, basically, like other side of the Earth or close to the Earth limb. The current mission operation concept is to cover the whole angular space in that area.
Any? I was wondering, how this would coordinate with the spare, future UV missions, or do you want to do simultaneous measurements?
Yeah, thanks. That's a good question. So this is not necessarily to need like co-observation with Aspera, or Aspera is going to. By the way, I'm the project scientist of Aspera, which the Hannah is going to give a presentation in the later session today, which is a UV or also another UV spectroscopic mission, and where the Aspera. The diffuse emission that Aspera is going to target is like brighter than brighter than like what we are going to do in the future. So for the Aspera, the current like maximum level of air glow lines, we already confirmed that would not be an issue for the Aspera. So this is like kind of solely for the future. When we want to detect something 100 times fainter than what Aspera is going to detect, then we realize that we need to know about this.
Okay,